Okay, guys, we're going to do 4.8. This will be the last section for our exam. We're going to have Newton's method on here. So the thing is with Newton's method is basically it's a technique that we sometimes would use. You would use it more in a computer class. If you, for example, in numerical analysis, I use Newton's method and we program the computer to do iterations. So this is an iteration method that is very calculation based, very heavy on using your calculator. So we're going to take a minute to do this, and we're just going to develop the idea of Newton's method. So basically what I'm looking for here is this C right here, okay? So that C right there on my graph, I'm trying to find where my big graph, where this graph, right? So this is my, y equals f of x, right? And I'm drawing tangent lines on each one of those locations. So let me kind of backtrack this a little. Okay, so maybe I shouldn't have used that big marker on hindsight. Okay, so this line is my f of x, okay? So we have this curve, and on the curve, we have all these points that we're calculating. Now, the thing about Newton's method is it tells you how to find the next point to get your calculation. So what we do is we're trying to find the root. We're trying to find the zero where it crosses the x-axis. So what we're going to do is we're going to kind of guess, and we're going to say, well, what if we had x1 and we found that tangent line? Would that tangent line cross at C? No, but it would get us closer to C. So if we wanted to find the equation of that tangent line, we would do y minus y1, but in this case, y1 is f of x sub 1, right here. And then we have equals m, but what's m? Normally m is f prime at the x coordinate you're using. That's our slope of our tangent line. And then we do x minus x sub 1, okay? So this would be our tangent line. And we're interested when it crosses the x-axis, so that means the height is 0. So then technically we know that this is 0 minus f of x sub 1 equals f prime of x sub 1 times x minus x sub 1. Okay, so we can clean this up a little bit. So this will be negative f of x sub 1 equals x f prime of x sub 1 minus x sub 1 f prime of x sub 1. So I just distributed, right? So now, if I want to solve for x, I can move everything over. So this will be x f prime of x minus f of x sub 1 equals f prime of x sub 1. Now I'm going to divide both sides by f prime of x sub 1. Divide by f prime, f prime x sub 1, f prime x sub 1. And let's see what we got here. So that'll cancel with that. So we're left with x. I believe I messed up. I believe this is x sub 1 right here, by the way. So please put that there. So this is x sub 1 minus f of x sub 1 divided by f prime of x sub 1. Okay, and this is equal to x. Okay, so we know that x is x sub 1 minus f of x sub 1 divided by f prime of x sub 1. Okay, now this, let's say we use this for our new x. That's this guy right here, right? So now we're going to say, well, let's do that again. And we would do the same exact process. Okay, we would say y minus f of x sub 2 equals f prime of x sub 2 times x minus x sub 2. Okay, So we're going to use this new x value, this one right here that we just got. We're going to use that for our new value, okay? And if we did the same thing, we'd get a new x, but this time it would be x sub 2 minus f of x sub 2 over f prime x sub 2. And we would keep doing this over and over to get the next value. So that's what Newton's method is all about. Newton's method is all about getting the next value, and each value is hopefully getting you closer and closer to C. And then you can decide on what margin of error is acceptable to you. So this is Newton's method. And again, as you guys could see, if I draw my tangent line, I cross right here, right? That'll be my new x. So if I look up and I go here, when I draw my tangent line again, this will be my new x, right? So this will be my new x sub 3, right? And then I look up and then I draw my line again. And guess what? I get my new x, but this time this x, my x sub 4, looks like it crosses the x-axis at the same location. So the tangent line crosses at the same location. So what Newton's method is doing, trying to do repeated iterations, get you closer and closer by using derivative tangent lines to get you closer and to where you want to be. So Newton's method, okay, uses iterations, and this is the formula for it. X sub n plus 1 is equal to x sub n minus f of x sub n all over f prime x sub n. Okay, so here's the thing. This will be our formula that we're going to use in an actual problem. Okay, so, and remember, x sub n plus 1 just means next n. So whatever the previous n was, if you add 1 to the iteration, you're on the next n. So xn plus 1, don't let that freak you out. That just means the next one, okay? And that'll come up in calculus 2 as well, okay? So let's look at an example. It says, example 1, use Newton's method to find an approximation to x cubed minus x plus 1 equals 0, okay? Correct to 4 decimal places. Okay. So the first thing I'm going to do is I'm going to sketch a graph of this real quick, just to kind of, maybe I'll do it over here. I'm going to sketch a quick graph, and it looks like if this is -2 and this is -1, the graph looks like it crosses. It's kind of doing one of these. Let's see, it kind of crosses right here somewhere. Oops, that's maybe a little too far. Maybe about there. Then it comes down, kind of levels off here a little bit, kind of comes down, and then it looks like something like that, okay? So we're pretty sure that the root is somewhere between -2 and -1. We're not exactly sure what it is. You know, it's probably some decimal or something, but what we're going to do is we're going to have to start off with our best guess. So, or something close. So I'm going to guess x1. I'm going to say start with x sub 1 is equal to -1.5. That looks like a good starting point for this, okay? So if we're going to use Newton's method, which is up here, we need the prime, okay? So we're first going to find f prime of x, and that equals 3x squared minus 1. So again, all I'm doing is I'm taking the derivative of this function right there, okay? So we have f prime of x equals 3x squared minus 1. So Newton's method says, if you want to find the next x, okay, so that would mean xn plus 1, that's going to be equal to x sub n minus, and then it says the function x cubed minus x plus 1 divided by f prime of x sub n, which is 3x squared minus 1, right? Everybody okay with this so far? So Let's clean this up a little bit. Now, technically from here, you could plug stuff in if you wanted, but sometimes we like to clean it up just to make it a little bit easier to enter into our calculator. So I'm gonna make common denominators. So this is actually over 1. So this needs a 3x squared minus 1. This needs a 3x squared minus 1. Okay, one thing I forgot to do is I'm supposed to be writing all of these with x sub n because we don't actually know which one we're using. Okay, so please take a minute to do that. Okay, so these all have subscripts. All these x's have subscripts of n. So this would now become, let's see here, 3x cubed n minus x sub n minus x cubed sub n plus x sub n minus 1 all over 3x squared sub n minus 1. Okay, so let's do a little cleanup. Oops. Okay, so we're just doing a little bit of cleanup. Okay, and let's see here. So we end up with what? 2x cubed sub n minus 1, I believe, over 3x squared sub n minus 1. Yeah, that looks good. Okay, so now from here, we're going to build everything. So now we're going to find x sub 2. So we already know x sub 1 is equal to negative 1.5. That's our starting point. That's what we've chosen. X sub 2 equals, let's see here, 2 times negative 1.5 quantities cubed minus 1 all over 3 times negative 1.5 squared minus 1. So when you plug that in your calculator, let's write out quite a few digits. Okay, so you guys might have to pause the video, plug this in your calculator. Make sure you use parentheses for numerator and denominator as 2 separate values. Okay, so I get approximately negative 1.344782,608. Now this is from a computer program, so it probably has more decimals than you do. So that's okay. So now this is my new x sub 2. So if I want to find x sub 3, I have to now take this value. I take this value, and that is what I plug into my x sub n. So now we're going to go 2 times x sub 2, and I'm just going to write x sub 2 so we don't have to write it out. Well, you know what? I'll do it for the first one, so you guys could just use it on your calculator. 4, 7, 8, blah 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 blah, cubed minus 1 all over 3 times negative 1.347826 blah 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 squared minus 1. When you enter that in, you should get approximately negative 1.325,200,39895. Now again, you might get slightly different than me because I believe your calculator only has so many decimals it can go to, but this is now my new x sub 3. Now the question becomes, how do you know when to stop? Well, they told us to make it accurate within how many decimal places? Correct to 4 decimal places. So that means I can't stop until 4 decimal places have not changed. So if you guys notice, right here we have a 3, and right here we have a matching 3. However, it stops, it's not the same after that, so we got to go again. Let's go x sub 4. So now we're going to go 2 times, and for sake of saving me on some writing, I'm going to use x sub 3, but you guys know that that's really the value to my right, divided by 3 times x sub 3 quantity squared minus 1. So what I did is I took this value, plugged it in there, and I take that value and plug it in there. Same value, okay? So now when we do this, we end up getting, again, negative 1.324718174, okay? So now look, now we have 2 digits that are the same, right? But it's still not good enough. It's still not quite right. Okay, so we need 4 digits that are the same in the first 4 decimal places. So we got to go again. So now we're going to go x sub 5. And remember, we can always find the next x. We can always find the next x by using the previous x. That's what Newton's method has promised us. That's what we're using right here. We're using this formula right here to find the next x each time. So you're just redoing this. I hope you can see how in computer programming this could be nice. So we're going to do 2 times x sub 4, whatever we got, cubed minus 1, divided by 3 times x sub 3 squared minus 1. And when you do this, you get negative 1.324791795724. Okay? But now here's the big important part. Now there's 4 digits here and 4 digits here that are identical. There's actually 5, but we only were asked to get 4. So I got these 4 and I got these 4 the same. That means that we are now close enough to the root within 4 decimal places. Okay? So then we are going to say that C, our root, is negative 1.3247. Okay? And that will be our answer. That is our solution. Okay? That's C we're trying to find. Okay? And we got it. We have to keep going. So remember, it's more of a calculator problem. The idea comes from calculus, but when you're actually doing it in practice, it's more of a calculator problem than anything else. Okay? There's another type of problem that we can run into. Okay? So let's do example 2. Okay? Now example 2 says, use Newton's method to approximate the square root of 10 correct to 4 decimal places. Okay. So what we're going to do is we're going to think of, how did the square root of 10 come to be? Where did it come from? Well, wasn't it originally solved, you know, it had to be the square root of 10, x equals the square root of 10, okay? Because we're trying to think of roots here, right? So how can we turn the square root of 10 into a root? Well, we can say x equals the square root of 10, but then that means that somewhere along the line, x squared had to equal 10, but that means somewhere along the line, x squared minus 10 had to equal 0. Because remember, that's what it means to be a root, that it's an x-intercept, right? It crosses the x-axis. It could be an imaginary root or a complex root, but then it wouldn't be in the real number plane, okay? So this is our formula. This is our f of x now. They didn't give it to us, we had to develop it, okay? So now we're gonna have to do the same thing as before. We're gonna do xn plus 1, okay? Oops, well, wait a minute, we actually need the derivative. So we have f of x equals x squared minus 10. So then f prime of x is equal to 2x, right? That's a nice clean derivative. Okay, and what do you guys think is a good place to start for the square root of 10? Well, I mean, the first square root that I know off the top of my head that's really close to the square root of 10 is the square root of 9, and the square root of 9 is 3. So I'm going to start with x sub 1 equals to 3. So that I feel like is a pretty good starting point. Okay, so we're going to use Newton's method. X sub n plus 1 is equal to x sub n minus, and then remember, let's go back up here to Newton's method. Newton's method says x sub n minus f of x sub n minus f prime of x sub n. So we're going to plug this in. Okay, so we're going to have x sub n minus, well, let me see here. What's a good way to do this? X squared minus 10 over 2x, and these are both sub n's. Okay, so now let's clean up. So this would be 2x sub n squared minus x sub n squared minus 10. No, it'd be plus 10 because we got to distribute the minus over 2x sub n. So in reality, this is actually what, x squared sub n plus 10 over 2x sub n. So I just made common denominators again, just to make my work a little bit easier. So now we're going to say x sub 1 is equal to 3, because that's a good guess or a starting point. So now we're going to do x sub 2. So x sub 2 would be whatever x sub 1 was, right? So we're going to have to plug in 3 squared plus 10 over 2 times 3. So that would be 19 over 6. So let's see what that is as a decimal. Well, I left my calculator inside, guys. I'll write down what the decimal is. So this is approximately 3.166666666, so on and so on and so on. Okay. So we could rewrite this as 3.16 bar. Okay. I guess this is it exactly, actually. Okay. So we have that now. Now we could use this for our x sub 3. So we're going to plug in 3.16 bar, and we're going to square it, plus 10 divided by 2 times 3.16 bar, right? And all I'm doing, again, you guys, is I'm using this formula right here. This is how we're creating each one. That came from Newton's method, okay? So now this should give me approximately 3.16228070, and again, it might be more decimals than you guys are getting. Not good enough, right? Because I need it to match 4 decimal places. So we're going to do this 3.1622 squared plus 10, all divided by 2 times 3.1622807. I'm not going to write it all out. Okay. And when we do that, we get 3.16227.766. Okay. Now this looks like good news for me, because I see these 4 decimal places are the same as these 4 decimal places. That means I have my answer. So we know that the square root of 10 is approximately 3.1622. Just cut it off. You don't round it. You just cut it off. Okay. So this is my answer. Now you could take out your calculator and you could do the square root of 10, and guess what you're going to get? You're going to get 3.1622, and then the rest will be different because they keep getting closer and closer. So that's what your calculator is actually doing, okay? Now really quick, you guys, I just wanted to show you a couple of pitfalls with Newton's method, a couple things that can go wrong. Okay. So suppose we have this drawing, and I'll do my best to try to draw it. So suppose we have this drawing like this. Okay, and I'm doing my best here. So let's say that I pick my x sub 1. I drew this kind of bad. Well, it's going to be a little bit of a pain for me to get it just right. Okay. So suppose that I pick my x sub 1 to be in such a way. So suppose I picked my x sub 1 to be right here. Let's say I picked that as my starting point. Okay. So remember, that means I go and look up, and then I draw a tangent line. Okay. I draw a tangent line. And then here is my new value. This is my x sub 2. And remember, we're trying to find this value right here. We're trying to find that value. So I got my new x sub 2. I look up, right? I go up here, and I now have this, and I draw my tangent line, and I get this, right? I get a horizontal tangent. That's not good, because that's never going to come back down. So I'm in a little bit of trouble here. I can't get back and keep doing more closer and closer iterations that are getting closer and closer to my root. Remember, I'm trying to get where it crosses the x-axis, but I'm never going to get there because now I'm stuck at a horizontal tangent, and I'll never get back down to the x-axis. So this is one thing that can happen. Okay, here's another situation. Okay, so let's say I have something like this. All right, and let's say, oops, let's say this goes up way over here. Okay. And let's say this time I pick my tangent to be like right here. And let's say that this is an asymptote right here. We have a little bit of an asymptote right here, okay? So let's say we pick right here. So I'm going to go up here and draw my tangent line. And this would be my new best guess for x sub 2. But you see, the problem is when I go to look up from X2, I will never touch the graph again. So once again, I cannot create my value, okay? Actually, yeah, that's one way you could do it. So you could end up going off the screen, like where you can't get back onto the graph, okay? So now there's another situation that's kind of the worst one. And this situation is this graph. Do that bad again. It's really hard to draw it just right. Okay. Okay, so what the idea is that, let's say we pick right here, and we pick right here. So let's say we choose our x1 to be right here. So that means right there, we're going to draw our tangent line. And it's going to go through right there. And then that means this is now my x2, right? And then I go back here. And here I draw my tangent line. And I draw my tangent line. Oops. And now I go right back through x1. So my x2 led me back to my x1. And then, you know, I go back up. It's supposed to look a little more symmetric than that, but I'm going to just keep messing up the drawing. But the idea is that my x2 brings me right back to my x1, right here. So I'm right back here now. I'm right here. And then when I look up, don't I end up back here again? And then I go down and I draw my line again, and then I go back up, and I just keep going in this circular motion. So I cannot get out of this loop. So this is an endless loop where Newton's method just keeps bringing me back to the same 2 points. And I never actually get to a closer approximation of the zero, of the root. Okay, so those are kind of the things that can go wrong with Newton's method. That'll be the last topic on our exam. So this will be what you can ask me about in class the next day. I'll probably only put like 1 or 2 of these at most on the exam. More likely 1, unless I find like an easy one and a medium one. And then we will be having our exam coming up. This will be our 3rd exam. And then the 4th exam, we'll probably spend the last 2 to 3 weeks of school covering. And then we'll have our 4th exam, and then we'll have our final the following week. Okay. All right, you guys, that's going to do it for this video. Just wanted to make a quick one for you guys to watch before class tomorrow. And please ask questions if you need help.